Thank you. Thank you for the introduction, and thank you all for being here today and for having me come down here and give a presentation on some of the research that we've been doing in my lab. So, as we said, I'm going to be talking today about infectious bronchitis control, vaccination strategies, application methods, and vaccines in particular. I'm going to start with application methods. At least in the U.S., and I think in most places around the world, broiler chickens are spray vaccinated with a live attenuated bronchitis at day of hatch. And in the U.S., if we are growing very large birds, then we may come back and field boost at 14 to 18 days post-hatch. In the U.S., as an industry, we are moving more toward hatchery vaccination only, trying not to use the field boost vaccination if possible. So that's what we're going to focus on today. Our systems in the U.S. look pretty much like this. You have a spray cabinet where your basket comes along a conveyor belt, moves through your cabinet. It is activated, it's activated by this laser eye, and then the vaccine is sprayed out of these nozzles down onto the chick. And when we're doing this, we use a syringe method for the most part in the U.S. So when the chick basket moves through the spray cabinet, these syringes are activated and the vaccine is forced through this syringe. But look at all of what's going on right here in this syringe. We have a large volume of vaccine moving through small openings here, moving through smaller openings here. We have a lot of bubbles forming in the syringe here in the vaccine. So all of this is decreasing our efficiency. We're creating a lot of turbulence here, which we now know will kill virus. And we're introducing air, which is reducing our total application volume. We're also forcing our vaccine out through these spray nozzles. And so it comes in as a liquid in a tube, and when it gets to the nozzle, we're aerosolizing it, putting it under a lot of pressure here at the nozzle to make it come out in this fan spray. So again, we're putting force and putting pressure on our vaccine. And ultimately what we use as our indicator of efficiency is how well is our box covered? Our chick paper, is it wet from side to side? Is it wet from front to back? And we use that as a visual indicator of how effective we are going to be at vaccinating our chicks. But as you may know, we have a vaccine in the United States called Arkansas. And it is probably my least favorite vaccine in the world. It's not a very good vaccine for lots of reasons, but it's a big problem in the US, and we have variants of Arkansas all the time in the US. And so we started out looking at Arkansas specifically and saying, well, why do we have so many variants? Why does Arkansas not protect the way it should against a field challenge? And so we have to remember one thing when we're talking about our vaccines. They are actually live viruses. We store them in the fridge, at least in the US, they're lyophilized, freeze-dried, we resuspend them in water or diluent. We may not consider that they are actually live viruses. And not only are they live viruses, they're enveloped, meaning they don't have a hard shell, they don't have a hard capsid protein layer, so they're very labile, you can very easily kill them or destroy them. So we wanted to ask two questions. Are we destroying the vaccine virus before we spray it? And maybe that's what's wrong with Arkansas. Or are we destroying vaccine virus when we spray it? Maybe that's the problem. So we did a couple very basic experiments, and we took an Arkansas vaccine and we took a mass vaccine as well, and we mixed them up and we held them at different temperatures. So we mixed them with cold diluent and kept them cold, 4 degrees Celsius. We mixed them with cold diluent and we let them warm up to room temperature over time. And then we mixed them with warm diluent, about 18, 19 degrees Celsius, and kept them at room temperature and did titrations every half hour to see what our vaccine titer did over time. What we found was if you mix your vaccine cold, 4 degrees, and you keep it cold, you do not lose titer. All the way out to 4 hours, we saw no loss in titer. If you mix it cold and then allow it to warm up, when you reach a critical temperature, after about 90 minutes, your titer starts to go down. If you mix it warm and keep it warm, immediately you lose 1 log of titer And after about an hour to 60 to 90 minutes, your titer goes down to 0. You have no virus left in your solution. So yes, in the system that we use in the United States, we mix these vaccines up. We usually don't use cold diluent. We put them out on the hatchery floor and they stay warm the whole time. Yeah, we're killing our vaccine before we even apply it. So we've started recommending that we need to mix our vaccine cold, at least refrigerator temperature, 4 or 5 degrees Celsius. Okay, we need to try to keep it cold if it's going to be used for more than 60 minutes or so. If it's going to be out on the floor for 90 minutes or 120 minutes, then we need to try to keep it cold when we're out there to extend the longevity of our vaccine. To answer the second question, are we destroying vaccine virus when we are actually spraying it? Does the process of using a spray cabinet destroy our virus? We designed an experiment where we took a chick box and we put these little tissue culture plates in 5 locations in the chick box, both corners, or all 4 corners, and the middle, and the size of each one of these wells is about the size of the head and neck of a chick. It's about the size, surface area of the chick that you're spraying when you're vaccinating. And we tested 3 different spray volumes, a 7 ml, a 14 ml, or 7 cc, 14 cc, and 21 cc application volume. Currently in the US, the standard is 7. That's our standard. And this is what a plate would look like after it came through the spray cabinet. So you can see we have multiple droplets inside each well. So that would be equivalent to what actually got applied to each chick, roughly. And then we did titrations. We wanted to measure how much virus was actually in that plate. How much virus got to the chick. And so in our 7 cc spray, the average volume was 120 or so microliters in each corner, 1, 2, 3, 4, but the middle got less. The middle got half as much volume. If we do the math on that, that means only 29% of our total application volume actually got down to the chicks. We lost 70% of our vaccine somewhere in the process. And if we look at the drop from this is the working solution, this is what we mixed up, and you can see we tested a Massachusetts strain, and we tested an Arkansas strain from 3 different manufacturers. So this wasn't a manufacturer issue, and it wasn't serotype specific because the Mass and the Ark both behaved the same. But if you look, the average loss in titer here was 1.5 logs. So we lost 70% of our vaccine volume and lost 1.5 logs of titer from what we mixed up to what actually got down to the chicks. Okay, that's a lot, that's significant. Looking at our 14 ml volume, so 14 cc spray volume. Same thing, we got more liquid to the chicks, but if we look at the percent, it's still only 30% or so of the total volume, right? So we increased the input, which increased how much liquid got to the chicks, but we did not increase our percent of total. But we decreased our titer loss by half. So we went from 1.4 logs lost to only 0.7 logs lost. If we look at a 21 cc spray, again, we dramatically increased our liquid volume getting to the chicks. Now, with this increase and this input, we're getting almost 50% of our volume down to the chicks, right? So we see a big jump up in our percent of total, which is very indicative of our efficiency. And we dropped our titer loss again in half, only 0.3 logs of titer lost from what we mixed up to what's getting to the chicks. Okay, now, so what this tells us from all of this is that even though we're losing a lot of volume, if you can get more liquid to the chicks carrying your vaccine, then you're going to be losing a lot less titer from vaccine solution down to the chick level. Okay, that's very important. Look at that. We reduced it by over a log. So if your vaccine titer was, let's say the release titer was 10 to the 5 EID50. By the time you mix it up and get it prepped for 100 doses per chick basket, you're down to 10 to the 4 roughly. You lose a log and a half doing a 7 ml application, now you're down to 2.5 EID50, and you're approaching the level where your vaccine's not going to infect anymore. Now, where did all this volume go? You think we put the volume in the syringe and it sprayed inside this cabinet, so where could it have gone? And so what we did is we partnered up with Georgia Tech University, a big engineering and architectural university in Georgia, to take some very high-speed, slow-motion video of the spray pattern coming out of the nozzle. All right, and what do you see here? You see we have our defined angle, but where is most of the spray? Most of the spray is right here in the center, right here. So we're not getting very much here, we're not getting very much here. And now, I don't know if you can see it very well, but look right here. If you notice, if you watch, right in this area here, in the top middle portion of the spray when it comes out, you'll see that a lot of that spray is coming out and then just blowing directly out of the back of the spray cabinet. Okay? It's not actually getting down to the chicks. And there are two reasons for that. Number one, if you have any airflow in your hatch room, so if you have a fan moving, if you're trying to cool down your employees, whatever, if you have any air movement, that's going to affect how those droplets move. Number two, with this 7 ml application volume, we're using a smaller flow rate nozzle. So a smaller flow rate nozzle is going to generate smaller droplets. Smaller droplets are not as heavy, they're more influenced by air movement, and they're easier to move out of the system. Now, I want to show you the 21 cc spray volume. Larger flow rate nozzle, larger volume coming through. Look at the spray pattern now. Look how much more even it is across the whole angle, right? We still have most of it centered in the middle here, but it's much more even all the way across. But look, see up in the middle here? We still have spray that's moving out, right? We saw that in our titer data. We still only got about 50% of the total volume down to the chicks. But that was enough to really improve our titer loss. So recommendations on spray application. What can we do? Well, if we're all really honest with ourselves, we know that our line speed is what controls our spray vaccination. We're not going to slow down our line to try to optimize how we vaccinate. We have to maintain a certain vaccination speed so that we can produce all the chicks that we need to. So your line speed is something that we're not really going to change, but you need to keep it constant. Whatever you need your line speed to be, set it to that speed and then leave it alone. Don't change it back and forth. Okay? It would also help if you actually know what that speed is, because there are technologies that are coming around in the future that are going to utilize the line speed as part of the parameters that we're going to use to, really set up these spray cabinets. But we've got this set volume that we have to use, at least in the US. So we use a 7, or we use a 14, or a 21, and that's where we are. We don't vary much from that. So what you have to do is, once you've set your line speed, decide what volume you're comfortable with. Most producers in the United States will not use 21 cc for bronchitis only. They say it's too much liquid, it wets the chicks, you're going to cool down the chicks and live a 7-day mortality or increase 7-day mortality. I think the jury's still out on that. I haven't seen enough data to convince me one way or the other. So if 14 is all you're comfortable with, then pick 14 and let's go for it. Once you've picked your volume, then you need to choose a nozzle. You've got to decide what flow rate you want on your spray nozzle. The larger flow rate, the better your vaccination coverage, okay? And then the last thing that you can change, really the only thing that you can change after that, is the pressure that you are using to apply your vaccine. So you have to adjust your pressure to match the speed of your line. You don't want your vaccine to run out too soon. You won't vaccinate all the chicks. You don't want your vaccine application to start too late or to go too long, because then you're wasting vaccine, all right? But if you increase or decrease the pressure too much, you're going to change the spray angle on your nozzle, right? And you're not going to get proper coverage, okay? And I'm going to show you some examples. So one thing we started using, I don't know if any of you were present for Mike Zarek's presentation on broiler ventilation, but he's introduced me to the infrared camera. And so we've started using infrared cameras to evaluate how well we're covering our chicks for vaccination. So I want y'all to take a look. Yellow and red is hot, blue and purple is cold. Okay, so when the chicks get vaccinated, they should turn blue or purple on the infrared camera because they're getting a cold vaccine. So chicks are nice and red, nice and yellow. Now watch the vaccine coverage. What did we see? Let's watch it again. That's too cool. Let's watch it again. What do we see? Look at the edges of the chick basket. What did we see? There's a lot of chicks there that didn't get vaccinated, right? Did you see that? In that study, when I challenged those chicks, they were not protected. Now, this is a vaccine system that has been optimized. This is one that we've put together in our lab. So watch the... Well, come on. Here we go. All right, watch the chicks come out of this system. It'll play on repeat because I like to watch it too. Let's watch it again. Look at that. All the chicks are vaccinated. I challenge this trial, 100% protected. Okay, this is a tool. It's a very inexpensive camera. It's something you can use in hatcheries during the production run. But it's a very good indicator of what your coverage looks like, how efficiently and how well you are covering your chicks with the vaccine. All right, now, we talked about the application. You gotta have good application, but let's talk a little bit about vaccination strategies. So there are two big vaccination strategies in the world, I would say. In the US, we design and use vaccines to induce neutralizing antibodies, which means we use serotype-specific antibodies. If we have a mass challenge, we use a mass vaccine. If we have an ARC challenge, we use an ARC vaccine. In the European Union and in a lot of other places around the world, even including some South American countries, we're looking at what's called a protected type strategy, where we use more than one vaccine of differing serotypes to try to protect against whatever the challenge strain is. And they may match, they may not. So if we, oh, there we go, the definition I just gave you. So if we look at the concept of protected type, you're using a type A vaccine, let's say. And so the bird will produce antibodies to that vaccine. And antibodies are specific and non-specific. You'll have some that bind directly to this neutralizing epitope. But you'll have a lot of vaccines that bind to just other regions on this spike protein, okay? They may bind very tightly, they may not bind very tightly at all, but there's a lot of stuff going on. Then when we give our second vaccines, remember we're using two serotypes, A and B, we're gonna get antibodies to the second vaccine that are gonna bind in other locations. They're not always gonna bind in the same place. And so the question becomes, can the binding of all these antibodies just at random locations on that major protein there, can that block enough of the infection to prevent a disease outbreak? This is a phylogenetic tree of just a number of different vaccines from the US and from some places around the world. The most common protected type vaccination strategy that has been used is with the genetic type 491 vaccine, which is in the 793B serotype. And if we look, I believe that one's on here somewhere. Yeah, right here. And then the MA5 genetic type vaccine that is in the Massachusetts serotype group. When we're doing protected type, we don't expect to see neutralizing antibodies. We still expect to get virus after challenge. We're not gonna completely stop infection. But what we're gonna do is protect the cilia. We're gonna protect the trachea. Bronchitis is such an economic concern, not because it causes mortality, not because itself causes a lot of indemnity, but It's because it destroys the cilia, which allows your secondary pathogens to come in, your bacteria, your E. coli, your Bordetella, things like that. And it's those secondary bacteria that cause air sac. Okay? So we need to protect the cilia in the trachea. If we look at this video here, see the cilia line, these epithelial cells. This is a video of a tracheal ring. This is actually a trachea from a chicken, okay? You can see the cilia moving. You can see things moving in the media here. They're beating very fast. They're moving mucus around. They're moving bacteria. They get trapped in the mucus. Everything's being expelled. This is a trachea of an infected chicken. What do you see? Nothing. Right, nothing's happening. There are no cilia here. No cilia beating. Look at everything that's just stuck right here. So that mucus is not moving. This is what causes the respiratory noise you hear in your birds when you have an infection of bronchitis. You hear rails or you hear snicking. It's because there's a buildup of mucus in the trachea. Okay? If the mucus is not moving, then whatever pathogens are trapped in the mucus are not moving either. And they can make their way through. They get into the bloodstream. Next thing you know, you've got air sac, right? So with Protectotype, we are trying to protect the cilia. And then to evaluate how well a Protectotype vaccination program works in the lab, we use a score. And essentially all we need to know is that anything above 50 is considered protected. If it's below 50, no good. Above 50, protected. So I'm going to show you the results of several different trials that we ran with differing vaccine combinations. So in this instance, we use an MA5 genotype and 491 genotype vaccine. And we challenged them with the strain called Georgia 08. This is a significant strain in Georgia. It caused a very high economic loss back in 2008 and then again in 2010 through 2012. No other vaccine combination that we had tried protected against Georgia 08. But this vaccine combination did. Remember, above 50 is protected. So then we tried it against some other strains, some other serotypes that may or may not be circulating in the field, but always have sort of a lingering presence. This Pennsylvania Wolgemuth 98. This strain is actually nephropathogenic. It's not even respiratory. Protected. Georgia 13 was a new variant of this Pennsylvania Wolgemuth that appeared in Georgia in 2013. Again, big economic losses. You see, 491 alone did not protect. But when you combine these two genotypes together, you get protection. Arkansas, ARC-99, that trial didn't actually turn out, but I've repeated this experiment, protection against Arkansas. Good protection against Arkansas. 491 Canadian version. So there is 491 in Canada now. Very good protection. Georgia 13 again, good protection. This is an Arkansas variant that's in Canada. Good protection. Every combination, every challenge virus that we have used in this Protectotype experiment, the MA5 and 491 have protected. We haven't found one yet that it hasn't protected against. It's been used a lot in Europe. If you talk to a lot of Europeans, they swear by it. They've used it in Italy to eradicate Italy 02. They've used it in other countries to eradicate QX and Q1. But in South America, it has actually been used already. This idea was used in Chile. Q1, there was an outbreak of Q1 in Chile. Everybody got together. They brought in 491 vaccine into the country, have been using an MA5 491 combination program since then. Q1 eliminated. It's a very good field study. So earlier in the week, one of the other speakers suggested that bringing a new serotype into a country is a bad idea. And on the basis of, if you say that as a blanket statement, then I would have to agree. But we have a situation here where this vaccine has been tested so many times and for so long. There's 20 years of research and field data to show that this vaccine and these vaccines together is a great combination. I would not recommend bringing in Arkansas. If you have an Arkansas problem, if you bring the Arkansas vaccine in, you're going to make your problem worse, not better. Okay, don't do it. But if you have an Arkansas problem, you can bring in 491, use the two together, and protect against Arkansas. Protect against ciliestasis. You're protecting the physiological activity of the bird. You have a Q1 problem. We've seen it works there. A QX problem. We know it works there. Now, the Brazil isolates, BR 1, 2, 3, and 4. Will it work against that? My guess would be yes. I haven't actually tested it, but it's worked against everything else that we've tried. So that would be my guess. But we know 491 is not licensed in most of the countries here, right? And it's not licensed in a lot of places in the world. It's not licensed in the US. In a lot of places, a mass-type vaccine is the only one that's available. So Massachusetts was the first bronchitis. It was the prototype. It's what everything else came from. Okay, we discovered in the late 1930s, turned into a vaccine in the 1940s. Mass vaccines, as I mentioned earlier, are all in the same serotype, but they have a different genotype in the S1. And so if we look at just a blown-up version of a phylogenetic tree, it's at H52, H120, MAS41, MAS Baudet. You see, they're all slightly different, indicated by these lines. If they were the same, they'd be on the same line, but they're not. They're all slightly different. And if you want to look it up, I've put the accession numbers in GenBank of these gene sequences. So these are publicly available. This isn't anything proprietary or secret. So all these gene sequences are a little bit different. We saw in one of the experiments where we used 491 by itself, we didn't get protection. When we added the MA5 genotype vaccine to our program, we did get protection. Well, we've tried this with a combination in the US too. And so here we're using the MA5 genotype with a Delaware vaccine, or a MAS41 genotype with a Delaware vaccine. Okay, if we look at all the parameters that we usually measure, respiratory signs, viral load, ciliestasis, against Arkansas, there were fewer respiratory signs with our MA5 genotype than there were with our MAS41 genotype. If we look at our Georgia 13 challenge, again, only one bird with respiratory signs, MA5 genotype, 4 birds with respiratory signs, M41 genotype. Oh, good. If we look at challenge virus recovery with our MA5 genotype, 9 out of 10 birds were still positive for recovery of challenge virus. Remember, with protected type vaccination, you are not preventing infection. You'll still find virus. We're protecting the trachea. We're preventing the secondary infection. But our viral load was 32.1. With the M41 genotype, 10 out of 10 were positive. Viral load was 30.11. There is almost a log difference in viral load here. That's a big reduction. So even though virus was still there, there was much less virus there. Ciliestasis scores, and this is dramatic. 60.5 with our MA5 genotype, 15 with our MAS41 genotype. 1 passed, 1 failed. So we know that MA5 will work, seems to work better than MAS41. And there are multiple reasons why, but we wanted to investigate one very particular reason. The differences in the spike protein. The spike protein is the major antigen. It's what the birds develop antibodies to. It is involved in attachment and infection in the host. And so we compared gene sequences between MA5 and a MAS H52, an M41, and an H120 genotype. And what we found was anywhere that you see a purple line, MA5 had a higher antigenic probability. That means the bird is going to respond better in those locations to an MA5 genotype than it would to another. Anywhere you see a yellow, it means that the bird is going to respond better to one of the other genotypes. Overall, you can see there's more purple on that graph than yellow. So overall, MA5 has a higher antigenic profile than these other genotypes. But this is just a line graph. This doesn't tell us a whole lot about the protein itself, right? Okay, so here's the protein. This is a predictive model of what a spike protein looks like on a bronchitis. You're going to notice there's 4 yellow blobs. These 4 yellow, these indicate amino acids. Those 4 amino acids are absolutely necessary for that virus to infect. You change one of those, no infection. So if that's what's involved in infection, then that's what the bird is going to want to block, right? So we should have antibodies being developed around that region. And so if we look at sort of a rotating model of this, you can see they all lie, all the amino acids that are critical for that virus to bind to the host are all in one location. Now, what happened here? We have 4 yellow amino acids. Now we only have 2 yellow ones. Where'd the other 2 go? Well, one's right there, but they're a different color. We took that linear graph and we turned it into a 3D model and said, so anywhere where it's red, like this, that means there is a huge difference in antigenic profile between an MA5 genotype and an M41 genotype. MA5 is much, much more antigenic. Anywhere you see a blue or purple color, moderately antigenic. It is more antigenic, but only moderately so. And if we look at the 3D model of this, again, we can see there are some differences in other places in the protein, right? We've got some here, we've got some here. But the majority of the differences in antigenicity, the majority of the differences in where that bird is predicted to make antibodies are right here, around this part of the protein that we absolutely know is critical for infection. So in conclusion, we know we gotta have proper spray vaccination. We're not doing a very good job with the system that we have. We gotta make some improvements. The MA5 and 491 genotypes, by far, you research the data, you research the field situation, they are by far the best protect-to-type vaccine strategy combination. And then when we look at MA5, the genotype itself, we realize that there are differences between the MA5 and M41 genotype, and those differences are in very critical locations. Now, can I say definitively that's why MA5 seems to perform better? No, this is all predicted structure, but these are the best tools that we have. This is the best we have to go on. And so with that, I'd like to thank Merck Animal Health for sponsoring me to come down here and give this presentation to y'all. U.S. Poultry and Egg Association is a granting funding association that provided a lot of the money to do this research. Poultry Diagnostic Research Center and Poultry Science, the 2 departments where I'm housed. A lot of students helped with this project. Eric Shepard, Christian Lapp, Giselle Rosa is actually an exchange student from Brazil that we had who did a lot of the spray cabinet work. Julia, Debbie, Christina. And with that, I will be glad to take any questions. Thank you.